morning, everyone. I'm happy that you come to my first lecture, even after the tough day we had yesterday. Everybody should have this exercise sheet. If not, there are some over there, and I also have some more here. It's mostly exercise 1 and 2. You can solve them after this lecture, and exercise 3 and 4 is like. But yeah, for now you can ignore this more or less. And yeah, let's just start with this lecture about introduction to what we very often abbreviate as TQFT. So TQFT stands for Topological Quantum Field Theory. Since it's such a complicated word, where very often we just say TQFT. Well, maybe first I should say that this title, this TQFT, it somehow is very scaring, right? I think like everybody is scared by this word. Mathematicians, especially, they're scared by the word quantum, probably also by the word field. Physicists, probably they're more scared about topological, maybe also about quantum. And I think anybody else, like people who are not doing math or physics, they're probably scared about theory. So everybody is scared. But so first message should be that it's not you should not be scared. It's something actually pretty simple. So the main idea somehow is that we will draw actually pictures. Very often we will just draw pictures, some diagrams, and somehow we will read off these diagrams some linear algebra data, some vector spaces and some linear maps. That's pretty much all. So we will draw a lot of pictures and we will do a lot of linear algebra. Maybe to start with just some motivations, or maybe one main motivation for each math and physics why we should do this. So for physics, I think the main motivation is that these kind of theories, they give you kind of a toy model for quantum gravity. But I should stress.
Sorry, did you hit record?
Yeah, I did. So I should stress it's really a toy model because in these models, as we will see, there's no geometry, there's no metric. Everything's just topological. And this actually, we'll see, this will simplify a lot. Maybe I should say that historically, these theories are introduced by Witten, so it really comes from physics. They were introduced by Witten in 1988, and actually the same year, Atiyah formalized, gave like a formal mathematical definition of what this is. So it's actually a very good example where within 1 year, both mathematicians and physicists, they somehow really work together. And so for mathematicians, this object, or these theories, they are also very important. And probably from a perspective, from the perspective we can take today is that for mathematicians, the main motivations why we should study these theories is that we get invariance for manifolds. It's really strange. Manifolds and other objects like knots, links, kind of objects. So you get kind of topological invariance for a lot of geometric things. Maybe I can make a small remark on this. Like in math, very often we try to classify things. For example, you can imagine you try to classify all kind of surfaces, like two-dimensional real surfaces. And, well, sometimes it's not easy. It's not necessarily easy to distinguish two objects. For example, if you try to, if you have a torus and then I have an object like this, probably you can imagine that these two objects are the same. Well, it depends up to what, but in the topological setting, you consider everything up to homeomorphism. So these two objects are kind of obviously the same. You can just pull it apart and deform it a little bit. But if I add another hole here, then probably you will see somehow that these two objects are different. But how would you really prove it? How would you really prove that these two objects are different? So somehow the main idea very often in these kind of classification problems is that you find somehow some numerical thing or some algebraic object associated to your your manifolds, which will not change whenever you change this object by a homeomorphism. And then when you have two different objects and the associated numerical thing is different, then you know that the objects have to be different. In this case, for example, it's this genus 1. So the genus, roughly speaking, is the number of holes. And here we have genus 2. And actually it's not difficult to show that whenever you take an object, a surface of genus G, and you deform it by a homeomorphism, this G will stay constant. And somehow, since these two numbers are different, we know that these are not homomorphic. They're generally different surfaces. So this is kind of like the basic idea of classifications and ideas of invariance. And we will see that these TQFTs, they naturally give you a whole bunch of invariants. In particular, if you try to understand the space of all, like a collection of all manifolds, collection of all nodes. Okay, so far so good. Don't hesitate to interrupt. So there will be 4 parts, and every part is around 90 minutes. They are not completely independent, but from time to time, I think you can wake up whenever you get lost. As you know, whenever you get lost, you should ask questions. The first part is about introduction to introduction and definitions. So maybe I should explain first why the name. I mean, if you give it a scary name, then there should be good reason for it, right? So why should it be topological quantum field theory? So probably I should start with why quantum. So why is there this name quantum? Because you will see that very often we'll have some Hilbert spaces. So we will have some Hilbert spaces. This is these Hilbert spaces. Here it will be a bit simpler. Here we will actually have vector spaces. And they will associate it to kind of systems. So each system gets a Hilbert space. And there's this very important idea that when you have two independent systems, then the total vector space associated to them is just the tensor product of the two parts. Hilbert spaces and tensor product for independent systems. I mean, of course, this is kind of very sketchy somehow. I mean, quantum mechanics is about much more. I think there's some more quantum features inside, but let's say for now, this is why it's called quantum. We deal with vector spaces associated to kind of systems, and we have these tensor products. Okay, so why is it called field? Why is it field theory? So the difference between like point quantum mechanics and field theory is that, well, it depends how large somehow your systems are. In field theory, well, the field is something which really actually is somehow everywhere. So you should associate your Hilbert spaces not just to points, but actually to something which goes over the whole of space. So the Hilbert space somehow, or these vector spaces are associated to the whole space, actually. The whole space. But when I say space here, I really mean space, like space as a slice of space-time. So there will be, so there's this idea that a field is spread out over the whole space. And very importantly, there's this evolution. So evolution gives you this kind of space-time. space time. And then whenever, like, I will often write it from left to right, so I have some space time like this. And like you have an initial data and the kind of the final data. So this is kind of a time slice. So this is space. Let's write another color maybe. Space at t equals 0. Space at t equals 0. Here you have space at t equals 1. So the TQFT is pretty much an assignment of, well, a Hilbert space, a vector space, to this. So you have some vector space at 0. Well, we have also some vector, some Hilbert space at 1. And then, so again, it is associated to the whole time slice because it's kind of a field. Field spreads out everywhere. And then evolution, well, evolution in quantum mechanics is a unitary operator. Here we will be slightly more general. This is just some linear map. This might be unitary, but very often we'll somehow forget about this. But somehow, whenever you define a TQFT, you can somehow put extra data in it. For example, you can equip all your vector spaces with some Hermitian form. And then you can ask these linear maps to be unitary. Okay, and finally, why is it topological? Well, it's topological because this linear map, this time evolution, does not depend on the geometry of this space-time. It only depends on its topology. Time evolution only depends on the topology of space-time. Not, in particular, not on a metric. So this actually makes things very restrictive. Yes, I mean, two spacetimes now are considered equivalent if they're just homeomorphic one to each other. It's very restrictive. For example, to get a feeling how restrictive this is, actually in this picture, like if I take it literally, I have like a one-dimensional object, and then I have a one-dimensional spacetime, some kind of cylinder. 0, 1. So if I take this picture more or less literally, then, well, this is homeomorphic to like a true cylinder. And actually, cylinder somehow is homeomorphic to like any kind of cylinder which has this. I mean, you can vary the height. The height here is not a topological thing. You can like vary this, so you can actually become arbitrarily close. Can be arbitrarily small, and this means somehow that the linear map you associate to this object is simply the identity. So here, this linear map is just the identity. It's just the identity. So now you could ask, well, but how can I get anything else then? Since there's only identity maps in this theory, how can you get anything which is not identity? Any ideas?
Yeah. You put some genesis on it?
Sure, exactly. You can, for example, take this. So if you have such an evolution, then now, a priori, this should be something which is different from that. Probably different. Okay, so this I think pretty much explains all the terms. So we have Hilbert spaces, tensor products, associated to time slices, and well, and it's kind of the time evolution only depends on the topology. So now we can become a little bit more concrete. So somehow I like this approach. Yeah, in this case, yes, yeah. If your space-time between two slices has trivial topology, somehow it's...
Is there some kind of physical meaning to having non-trivial genus?
Yes. I mean, I could say it now, yeah, somehow, yeah. Yeah, I think we'll see this later. But again, I mean, it's just a toy model, but I think even to this you can get to the meaning. I mean, yeah, actually, no, I can tell you now. Like somehow, well, this is space, but you could also consider it as a particle. So you have kind of a scattering. And if you look in the middle here, actually you have two particles. So somehow you have actually kind of a particle which splits up into two particles and then they merge together again. This is kind of the only non-trivial thing you can have in these kind of theories. You have like creation, annihilation of things. More questions, yeah.
So why does this map on the cylinder have to be the identity?
Well, my argument, yeah, I agree that my argument was not completely maybe convincing. Well, I mean, from the physical thing, you would say like, whenever you have some time evolution, if you take the limit when t goes to 0, then somehow this should go to the identity, right? It's not discontinuous. And now from the topological perspective, all these cylinders, as long as they might be, or as short as they might be, they are just the same.
Okay.
But there's actually an even better argument, we will see it later, why this has to be the identity. Okay, so I said that I like this kind of, like when you learn a new subject, I mean, you could start by giving the definition and then think about the definition for a long time. I like to give you like kind of different layers. This was like layer 1, just explaining the name. Layer 2 will be a bit more details, and then layer 3 is to give like the definition. Okay, so probably I will repeat some things from time to time, but I think this is not bad. So basic ideas. So as I already said, space. Well, what is space? Space is a manifold. And to each manifold, we associate assign a vector space. And I will call this V of M. I think I already did more or less V of 0. Well, there's this big V. And like you can think about it as like, yeah, either the space of all states or the space of all fields. Could be something like L2 of M, like this. And then there's this time evolution. Change the boards. This is kind of the very important thing. This time evolution. And kind of mathematically, what these time evolutions are, it's something which is called a cobordism. So this is actually just a manifold which has one dimension more. Like if this is of dimension d, this is of dimension d minus 1. Cobordism B, manifold of dimension d, like one dimension more. And it has boundary, and somehow the boundary even plural boundaries. And somehow you have kind of the notion of an incoming boundary and an outcoming boundary. So it's exactly this kind of picture I already drew. Such a thing, and then you have the genus like this. So this is B. This is M0, M1. And so you have some notion of incoming boundary and some notion of outcoming boundary. And so what the TQFT associates is exactly this linear map. So you have a linear map, you have V of M0, V of M1, and this linear map, I will call it with a small v, it's a small v of B. So you have an assignment of a vector space to a manifold of dimension d minus 1, and the assignment of a linear map between two boundaries, the incoming and the outcoming boundary, for each manifold, which is kind of this cobordism. Cobordism. And well, what is this thing? This is a linear map between V of M0 and V of M1. Yes.
M0 and M1 are just the copies of N, I guess, right?
It depends. They could be different.
But like at this picture, there are also genuses at B. Like how do they occur? Like
B, so the cobordism is any manifold. It's any manifold which somehow interpolates between these two.
okay.
It depends how you look at it. If you first give me M0 and M1, then you look for a D plus. I mean, to look for a manifold with one dimension more, which has M0 and M1 as boundaries. You could also just start with any manifold of dimension D, and then somehow say this is like the incoming one, this is the outcoming one. So you might, or you should actually ask one question, at least the mathematicians among you should ask the question like, how do you distinguish between incoming and outcoming? If I just give you a manifold which has a lot of boundaries, how do you decide? So to distinguish incoming and outcoming, what we will do is we actually work with manifolds with some in orientation. So we somehow, everything is oriented. So oriented manifolds. So what does this mean? So on my picture, what I could do is the following. Well, in 2D, it's very easy. Somehow, it just gives you the notion of some kind of, well, either you say what kind of, what to say. If you have an n-dimensional vector space, there are two kind of bases. If you consider two bases as being equivalent under some rotation. In 2D, you have like one would be this. This is like your first vector and your second vector. The other kind of orientation would be to swap them, to call this the E2 and this you call the E1. From the matrix perspective, like you have this group of rotations, which is SO of your vector space. And SO means that all your matrices have determinant 1. And so this actually allows to like identify all bases apart from those you can get from some matrix with determinant -1. And actually in 2D, it's actually, you can just draw this kind of picture. You can just say, well, it's kind of a notion of turning around. You either go clockwise or anti-clockwise. Typically, I would take this mathematical trigonometric orientation, which goes anti-clockwise. But it's the choice. And well, on the boundary, it's the same. So now everything comes with an orientation. So let's say, for example, let's see that I get this right. So for example, I will orient M1 like this. And, well, yeah, so if it's one-dimensional, then actually it's just like if you turn left, you turn right. So on this side, I will take this orientation. So all your data comes with an orientation. And then there's this, you can, when you have a d-dimensional manifold with boundary, you can induce the orientation of the big space to its boundary. So you have like this notion of the notion of an induced orientation. This is maybe it's wet. So just disintegrate. So a cobordism with orientation induces orientations on the boundary on its boundary. And then you can simply compare whether it's coherent with the orientation you already have or not. So in 2D, it's very easy. In 2D, like you have this kind of turning thing, it turns anti-clockwise. Somehow you take this object and you just go close to the boundary, and then somehow you see that the induced orientation goes like this. And on the other hand, like if I go close here, my induced orientation goes down here. And then you compare. So the red arrow goes the opposite way. So actually M0, the orientation of M0 is like not coherent. Whereas here on this side, this is coherent. Yes?
I'm a bit confused about your arrows, I think. When you draw the curly pink arrows,
Yes.
is that like going around the manifold on the blackboard? Like
No, it's really local. Like around each point you have this kind of small thing. Yeah, so yeah, no, this is very local. It's very local. Because like what is actually this is a coordinate system, but actually a coordinate system is something you can consider at each tangent space. It's very local. Yeah, I mean, in 2D I really like this kind of curly thing because it's very, you really immediately see somehow how it induces orientations on the boundary. On a more formal way, how should you tell the story in a more formal way? Well, you take your kind of well-oriented basis and you take the first vector and you push it such that it is like normal to the boundary. And then you have like one vector less, and what remains gives you this orientation on the boundary. So here you would see it goes up. If you do the same, well, if I want to have it normal, then I should turn it around. This is E1, so this goes down. This recipe is actually more general for n dimensions, d dimensions. In d dimensions, you take this d-dimensional basis, and you turn it. I mean, you can turn it by rotations, and you choose this rotation such that the first vector is normal to the boundary, and then the remaining d-1 elements of your basis, they define a basis on the boundary. This is this induced orientation. So, yeah, I agree that this is like the first subtle point of the whole story, but actually you will see that you will not really use them so much because somehow you will just draw the incoming things on the left and the outcoming things to the right, and actually will not draw the orientations anymore because somehow, I mean, you could deduce it somehow from it. And so there's this notion, of a negative boundary of B, and the notion of a positive boundary.
Alexander?
Yes.
I have two questions. So first of all, if you want to define the normal field on your manifold, don't you need a metric? I mean, so
no, you don't need this, but it's a good point because you might need some kind of embedding, and of course we don't want embeddings. It's a good question. How do you? No, okay, no, you don't need an embedding. So what happens is that, as I said, these pictures, like they live in the tangent space. If you take a point at the boundary, somehow from the big perspective, like from the big manifold B, you have a tangent space. That's also as M1 somehow gives you somehow a subbundle, gives you a subvector space. So now actually you just have a d-dimensional vector space, a d-1 dimensional subspace. Somehow you just turn your basis such that E1 is orthogonal.
Yeah, but how do you define orthogonal?
Well, you can choose any, like on this vector space, you can choose any metric. It doesn't matter. Because at the end, the only thing which counts somehow is like how these vectors, like in which order they come. And the order somehow does not depend on this. Yeah, maybe you could say it differently. So you have E1, E2, E3, for example. You just take the plane generated by E2, E3, and then you just use your rotations such that this plane coincides with like this subspace, and it's all actually. You don't really need actually to be orthogonal or something. Yeah. You just need that this somehow lives inside. Okay?
Yes.
Second question.
Yes. So from a more physical perspective, how do you decide on the orientation of B?
Okay, good point. I would guess that taking this orientation, well, I mean, if you count, like if you give me an orientation of M0, B, and M1, if I change all three at once, this will not change somehow what is incoming, what is outcoming. I would say that physics is invariant under this. But if you just change the orientation of B and you keep the orientations of M1 and M0, it means somehow that you reverse what's considered the past and the future.
Right.
And then it's more subtle. Would you say that physics is invariant under time inversion? This is more subtle. Maybe it's also invariant under this, but maybe not. But somehow the overall choice is kind of irrelevant. That's why actually we will draw pictures without this orientation. We'll just draw incomings and outcoming stuff. More questions? Okay, so I said there's kind of this notion of there are two kind of boundaries. Like one of them should be M0, and the other one should be M1. So this is kind of a negative boundary. Well, yeah, it's like the negative boundary. Can you read actually this color?
Yeah.
So what does it mean? It means that it's kind of the boundary components where the induced orientation is not compatible with the given one. And this one is the other. It is compatible. Well, again, I mean, this is like technical things which are not that important. Somehow, the way we will draw these pictures is you will read them from left to right.
Just to make sure I understand.
Yes.
So when you say covariance B,
Mhm.
does it already encode the data of the given orientation of M0?
Well, if you just say cobordism, no. But actually, what we will do, we always consider oriented cobordism, oriented manifolds. Like when I said space is a manifold, you should actually think about it as an oriented manifold, and you have oriented cobordism. So just maybe to make it like an example. Well, one example is kind of the cylinder. Let's draw these orientations once, but then forget about them. Let's say it's oriented like this. So if I draw it like this, it means that, well, it induces an orientation like this, and it induces an orientation like this. But the boundary comes with this orientation. So it is anti-compatible on the left and compatible to the right. This is, input, output. But you could imagine what happens, for example, if I change this pink arrow. If I change the orientation on this boundary, then suddenly it's not an output anymore. It becomes an input. And so how should I draw the picture, actually? How should I draw the picture with this arrow reversed? Okay. Yeah, now you have two inputs. right? And, well, it's still the same topology, so it's something like this. Right, so now I can still have my arrow like this. So close to this boundary, it goes down. Close to this boundary, now it goes down as well, but my orientation is there, going both. So now somehow my income, M in, well, let's give it a name. So this is M0, this is M1. But now the incoming boundary is actually the union, right? It's like the union of these. And what's the outcoming manifold? The empty set, yeah, there's no boundary on this side. And so, what are the vector spaces associated to these objects? So the vector space associated to the incoming, so there's a union of two things. So you should think about every boundary component as a system. So this is one system, this is another system. And since they are disjoint, they're independent. And so it will be the tensor product. Tensor product between these two. This is typically, this is exactly when disjoint boundary components appear, you have typically this tensor product. And now, question, what is the outcoming vector space?
It's just the field of the vector space.
Yes, exactly. Let's call it K. So what is K? So actually I have not told you this earlier, but of course whenever you have vector spaces, they are defined over some field. So K here is the base field. Like we consider K vector spaces. And what's most relevant, especially for quantum mechanics, would be that K equals C. You can always, in your head, you can always think about C. Like complex numbers. But you could also imagine, I don't know, doing some real quantum mechanics or something. You could put an R here or some other field, maybe rational numbers or any field you like. And so why is this true actually? Yeah, so when you have nothing, somehow nothingness is still something. So the base, why does the base vector field come here? There's a good reason. When I erase the board, I let you think about this. Okay, some answer to this? Yeah, Hakim?
Physically, because there's a U1 symmetry, you can always change the phase.
Sure, but you could have like, I mean, you have a U1 symmetry on any vector space once you have a basis. I mean, even without a basis, right? You can just multiply. I mean, you have if you have a C vector space, you always have an action of U1. Let's not think about this kind of trivial vector space. Well, you could maybe argue that this is the most trivial boundary you can have, and this is the most trivial vector space you can imagine. But there's a better reason for that.
If you take the union of any space with the empty space, this tensor product with the...
Very good, very good. So yeah, empty sets are everywhere, right? Like you could say actually here the input, I said that this is M0, but it's also M0 plus nothing, right? And so since we have this kind of axiom, we'll describe more in detail, that you have a tensor product structure. So whenever you have M0 union nothing, well, by the kind of this axiom of quantum mechanics, these two, they're disjoint. So this should be V of M0 tensor V of nothing. But of course, this is the same as V of M0. So you need actually, so this thing should be something such that when you tensor with it, it gives you the identity. And this is actually only the base field, the only vector space which has this property, means that this is K tensor any vector space, K vector space, gives you back this vector space. Okay, great. So now we have a pretty concrete understanding what these TQFTs are. Vector spaces, linear maps, well, some kind of orientations, empty sets. Very good. And there's one ingredient missing, very important as well. Well, whenever you have time evolution, well, we spoke about like T0 and T1, but of course you can also go further. Like what happens if you now take several time evolutions, one after the other. So mathematically what happens is there's some gluing going on. So as a picture it would be this, like you have something, some cobordism, and you have some other cobordism. And what you do literally is you glue them together along some boundaries which coincide. So here you will just get this picture, pointing here to here. And you still have kind of this. You glue them together. So here you say you have V of M0, V of M1, V of M2. Here at the end we just have V of M0, V of M2. So let's say you have a first linear map here. Let's call it, I don't know, F of 0, 1. Here you have another map, F 1, 2. I think it's very natural, also from the physical perspective, of course, if you first evolute and then you have another evolution, then the combination of them is simply the composition of these maps. It's just a small, it's just a writing detail that you should write it like this, F12 composed with F01. Right, this is always the same issue with this notation. That, we somehow declared that we should read compositions from the right to the left. First apply F01, then apply F02.
Sorry, about the gluing. How do you do the orientation?
Yeah, that's a good point. We will come back to this. I think we'll come back to this. But, so you only can glue outcoming boundaries with incoming boundaries. And for now, what I just want to say is that you have this kind of conversion of maps. Okay, I need to say more at this point. No. Yeah, but we will come back to this. Good. Yes.
So at first you consider your two surfaces as independent?
Yes.
And so in principle you could also have another gluing where instead of gluing the M1 with this the other one, you could also reverse it.
Yeah, okay, but this is somehow the question he asked. Somehow you can only glue two things which are literally homomorphic and somehow where the orientation are not compatible one with each other. So this would go down, this will go up, and then you can somehow glue them.
But I mean, so you could have the two holes on the left and then the one surface with the one hole on the right as well, no?
It means concatenating them the other way.
M1 is the same as M2, sure.
Well, you can also glue them like this, maybe. Yeah. Yeah, the axiom somehow tells you that whenever you have like M0, M1, and another M1 and M2, then you can somehow glue them. But if you somehow identify M0 with M2, you could glue the other way.
Sure, okay.
And so, before giving the axioms, there's one more very important thing, is, well, here we glue things together, but actually gluing things together is actually more or less the same thing than decomposing a more complicated object. If I take this and I want to go back, well then somehow I take this big space-time and I cut it somewhere. And this is actually really one of the most important ideas in TQFTs, is that you can decompose complicated stuff into very simple stuff. So, but also we have gluing, but also decomposition. So if, for example, I could take the same example, but let's just take something else. If I take this example, so let's say we have f v of m0, v of m1, then actually I can decompose it somewhere. For example, I can decompose it here. I will get some v m1 half. So the index somehow is the time. I have time 0, time 1. So in the middle I have t time 1 half. And then what happens is that, well, a TQFT gives you this linear map. And decomposition means that this linear map actually factors through this other vector space. Factor means somehow that this, well, for those who know, this diagram commutes. And this is really the powerful thing about these theories. Like, you decompose complicated things into simple things.
So maybe you're about to go on, but a priori, how do you choose a vector space? You just like
This is the data of the TQFT. TQFT, you have like this, you have the list of all possible d-1 dimensional manifolds. It associates something to them.
like at each slices, whatever you get.
Very good point. And this is actually, I think, very physical interpretation of this. Like you have some space-time. You can actually take any slice. You can take any slice, like also like this, or you take any slice. It defines you some kind of a space. And for every space, you have actually a vector space. You have a symbol space. And then this axiom, it holds for any kind of slice. This makes it very, very restrictive. I mean, very, very strong. Here we cut, for example, here, but we could also cut at this point. And yeah, what happens then is that we have actually two boundary components. So again, this really allows us to decompose complicated objects to simple objects. Actually, there's like a there's a finite, even very finite list of simple pieces. So somehow you can glue complicated things from very simple pieces. So somehow once you know the simple pieces, what we will do, or what a TQFT actually does, is when you draw somehow your cobordism, and then you read it, you literally read it from left to right. Sometimes I also write it from bottom to top, depends. And then somehow, yeah, you start reading here, and then you stop whenever something non-trivial happens. Like at the beginning, for example, if I read here, and slice here, well, it's a cylinder. Cylinder is just the identity, nothing happens. At some point, something interesting happens. And this kind of interesting piece should be some elementary building block. So this corresponds to some linear map. So I know what this is doing. And then I go on. I go on and I go on. So either I just see identities or I see something interesting. And what I do at the end, I just compose all these maps.
The interesting thing only happens at like critical points then?
In this picture, yes. Yeah. Well, actually, even in general, yeah, that's true. Yeah. Okay, so maybe the last thing before getting more details is, once in some talk, somebody gave a slogan, and I actually like this. The slogan, well, it's more like for mathematicians, the slogan is that the TQFT is kind of a representation theory for manifolds with cobordisms. Representation theory. Of manifolds with boundary and cobordisms. Representation theory is typically you have a group and you want to write the group as a matrix on the vector space. Whenever you have group homomorphisms, they should correspond to some linear maps. So here's pretty much the same. Any manifold gives you some vector space, and then its cobordisms somehow give you these linear maps. Okay, questions?
You can always find the TQFT.
Yeah, good question. Well, we will see one-dimensional and two-dimensional examples. I would think that there should be some kind of a trivial TQFT, which just assigns always identities to everything. Is there a kind of non-trivial TQFT for any dimension? I'm not sure, actually. Maybe this is a hard question. Yeah. Yeah, it's a good question because it's so restrictive, and maybe there's nothing actually there. But you will see, like in 1D and 2D, a lot of examples. And somehow they're encoded in some algebraic structures. Okay, then let's go to the formal definitions. So somehow, I mean, with all these pictures, I think we have actually already developed kind of a good intuition what a TQFT is. So you could probably more or less forget about the formal definitions, but somehow just to check that we can actually write these intuitions in like formal terms. Well, probably I will not be that formal than mathematicians should be, but okay. So this is due to Atiyah. Here's somehow a list of axioms, what such a theory should do. Okay, so a d-dimensional TQFT. What is this? The definition. So it's an assignment. For those who know what it is, it's a functor. So giving what? Giving two things. It gives a k vector space. K vector space V M to each, what we said earlier, oriented manifold of dimension d minus 1. And actually you have to ask this manifold to be without boundary, closed to each oriented closed d minus 1 dimensional manifold. There's a small shift. If you really look in Atiyah's paper, he would say this is D. And but nowadays we have this shift. Like Atiyah speaks about like zero-dimensional TQFT and one-dimensional TQFTs. But now we will call a one-dimensional and a two-dimensional TQFT. Well, that's the detail. And so you have k vector spaces, and then it assigns a linear map, or actually it assigns a vector, which I call small v of b. So this vector lives in a vector space. In which vector space? Well, it lives in the vector space associated to the boundary of b. So to each oriented d-dimensional manifold with boundary. So before giving, like, there are conditions, right? So it's an assignment which satisfies some conditions. Maybe first I should say, well, this formulation seems kind of different from what we did before. Before we had this incoming boundary, the outcoming boundary. Actually, Atiyah here is very clever. Atiyah is very clever because he uses actually some isomorphism. So whenever you have a map from V, like whenever you have an element, linear map from V to W, this can be actually seen as, this is isomorphic to V star tensor omega. And so somehow, if I have a map from what I called earlier the negative boundary to the positive boundary. Sorry, the vector space is associated to them. I should write it maybe like this. So before I had the vector space associated to the negative boundary, vector space associated to the positive boundary. So this is actually it's actually just some vector space. And actually, one axiom, we will see, one axiom tells you that if you change the orientation, it gets you to the dual. So this actually is isomorphic to V of so when I write del B, it's the boundary with its induced orientation. So we have the kind of the piece on which this orientation already coincides with the boundary orientation. And if not, then passing to the dual, somehow you can change this orientation.
Are we assuming the association of vector spaces is finite dimensional since the double dual is not necessarily the same space?
Yes. Good point. Yeah, I think in his definition probably everything is finite dimensional, yeah.
Okay.
Which makes it a bit unphysical actually, but yeah. Maybe let's add here finite dimensional. Probably there's probably some extension which is not finite dimensional. Yes.
Is the last point what you meant with the kind of twisting?
Yes, you can see it like this, yeah. But actually we will not really use this. I mean, I really like to think about linear maps because it's really time evolution. But you could always, we can always somehow change things and just make it a vector somehow.
There's a question.
Yes. Sorry.
Do we assign the same vector space to manifolds that are diffeomorphic?
Yes, this is one of the axioms. Yes. Yeah, we'll go there. Yes.
So the fact that this is a vector, you're saying in combination with this remark,
Yes.
it uses this linear map that you had before.
Yes.
This hom that you wrote on
So
the
a
first.
vector in this thing is a linear map. It's literally this. But again, I mean, for the sake or somehow to reproduce Garcia's axioms, I will use this, but later on we'll always use the linear maps. So the definition is not finished. I just told you what we assign to each thing, and then such that the following axioms are satisfied. Well, first axiom is exactly answering your question that V of M and V of B only depend on the topology. Only and topology of M and B and B. So like in more fancy terms, it would mean like if you have two manifolds and some diffeomorphism between them, then this induces kind of an isomorphism between the vector spaces.
Can I also ask then, are we on smooth manifolds or just topological manifolds?
You should look at the Atia's paper, but maybe he writes smooth somewhere, but since everything's topological, no, I think no, I'm pretty sure no, it's topological, so everything's it's just homeomorphism. But of course, you could imagine something like diffeomorphism, which somehow from dimension 5 on makes a difference, or dimension 4 even on. But but details. Well, this makes it really topological. The second axiom is somehow what I've said here. Whenever we change orientation, V of M star is V of M star. So here M star is manifold M with reversed orientation. And here the star is really the dual space. So since it's an assignment which gives you for all oriented manifold something, well, in particular, you can take the same manifold, equip it with one orientation or with the other, and they are linked through this duality. Okay, then we have two more axioms. Well, one we have already seen a lot. It's whenever you take the disjoint union of two manifolds, seen as boundaries, right, as spaces, then this is a tensor product. It's the tensor product structure. And the only thing which is missing now, the only axiom which is missing is this gluing axiom. The gluing. For the gluing. Which says the following. Well, if I want to write it in mathematical terms, it's something like this, like the vector associated to a manifold which is the connected sum of two pieces, and this connected sum is along some manifold m1/2. Well, actually, I should connect 0 and 1 then. Then this is simply, this is a, well, well, actually, well, now I think about it as a vector, sorry. I don't think about it as a vector, I really think about it as a linear map. And then it's the composition of V of V2. This is V of V2 composed with V of V1. So the picture which goes with it is exactly the picture we had already. So we have M0, M1, somewhere in the middle, M1/2, boundaries here, and then you have two coordinates, B0, B1, and this symbol here, mathematicians call this the connected sum. But literally, the connected sum is the gluing. Like you have two pieces, and they agree on some middle piece, and you glue things together. And somehow you specify along which thing you glue. So this is this M1/2. And again, so this is a new cobordism, the gluing of these two. And seen as a linear map, this is just the composition of first doing V of V0. And then V of V1. It's literally this idea of reading linear maps, V of V0, V of V1. And this holds for all possible decompositions like this. That's why you can actually redecompose this map into even smaller pieces. Yes, Danilo?
How do I interpret this in terms of V just being a vector, an element, or a vector instead of a homomorphism?
Yeah. Well, somehow what happens is, for example, this, if you... Yeah, it's a very good question. I will maybe draw a picture. I might be able to draw it even here. Let's see. So what you will do is, you will draw M0 and M1/2. So remark, question. So how can you like reconcile these? So you can also draw it like this. You have M0, M1/2. So you have your first cobordism like this. This is B0. And then, well, the second cobordism should be like this then. This is M1. And somehow what happens then is that you have, well, you have a vector. Yeah, we'll draw actually a lot of pictures like this. So this, of course, is the same as the other one. I just find it a little bit. And so now what happens is you have a map. Is this correct actually? Maybe I should try the other way around. What I want to say is something like you have a vector. Oh no, yeah, no, it's good. So you have a vector which is in this vector space. Well, since I turn things around, it's a dual. And I combine it with something else, which is V of 1/2 tensor V of M1. Well, no, sorry, if I want to be exact, M1 also has the dual, right? So we said that we have like dual to something. So this comes with duals. These are the same. And actually the gluing makes, well, first of all, they are somehow disjoint. You should think about this first being disjoint. And what the gluing really does is contraction. It's literally, you apply this linear map to this vector, and then they disappear, and you have a map from M0 star to M1.
Shouldn't the dual be on the other M1/2?
No, because if you do it exactly, then I mean this is an
in this picture.
This is an incoming for B0, but it's an outcoming for B1. So the incomings come with duals, the outcomings come with.
Yeah.
This is why you can somehow glue. So if you don't understand this argument, it's not very important. We will actually see it again in the probably third lecture. We'll see this again that we'll see again that actually TQFTs, very often you can see them as tensors because you have like vector spaces and their duals. And kind of gluing is this kind of contraction. At least the physicists know from GR, from general relativity, when you have like big tensors, you can sometimes contract indices. This is literally. More questions?
Why the VM0 is also
Why do we have M0?
Is also inverted. Is also.
Oh yeah, because of this this thing. Like whenever my favorite perspective is to say that it's a linear map between the income and the outcome. But actually, income and outcome, this is equivalent to saying you take just a vector in the incoming dual tends to the outcome. So if you take B0, the income is M0 and M1/2, so they come with duals. Well, technically it goes to nothing, right? And the other one, the income is nothing, and the outcome is M1/2 and M1. More questions? Well, this is really just the formal definition of actually everything we had before, just put more abstract stuff on it. But now that we have kind of the more formal things, we can also check. That's not a good one. We can also check what we had earlier observed. So let's say some kind of easy consequences. Some easy consequences from these axioms. And then I will give you like the easiest example, which is like one-dimensional TQFT, and this should be the end of the first lecture. Easy consequences. So the first one is, well, yeah, if the TQFT is non-trivial, which means that it's not only it is not assigning like identity to everything, then the linear map associated to the cylinder, so the cylinder is the cobordism, which is literally your manifold cross 0, 1. This should be the identity of the vector space associated to that. And now actually we can prove it, because, well, if you take any cobordism, I will always draw more or less the same pictures, but this is now d-dimensional. You can always add a cylinder, right? You can always add a cylinder. So let's say this is M0, M1, M2. But topologically, this, you have done nothing, right? So this topologically is the same. Like topologically is the same as, well, just this. M1, M2. But now we know that like reading these pictures means that you have some linear map here, which you compose with this linear map. And this should be the same as just reading this linear map. So it means that the linear map we have here, composed with anything, should be the same thing. So it can just be the identity. Oh, actually, non-trivial, I think, means even worse. I mean, you could imagine that your maps are all going to 0. Literally 0. And then probably you can assign, like, I mean, it means that there are some, I mean, you could, for example, imagine that whenever you have a non-trivial topology, this gives you the 0 map, and only the cylinder is something interesting. Well, then probably this should work, but that's somehow considered trivial. Yes?
Can it be the last picture from M0 to M2?
Yeah. Oh yeah, you're right. Yeah, you're right. Yeah. So it's more like M0 and M, yeah, and then you somehow deduce that M0 and M1 are like literally the same. Yes. So they are the same. So maybe I should try to write things down. So yeah. So if I would write it down in an equation, it means that if I compose 0, 1 with 1, 2. This gives me 1, 2, or 0, 2. Well, now it looks less obvious. Now it looks less obvious. I wanted to say that it's 1, 1, 2. 2. No, I say that this is. I want this to be 1. No, I want this to be 1.
Maybe if you draw like the M0 after M1, so you just go a tiny bit and then you...
Oh, I see what you mean. Yes, maybe you're right. Yeah, maybe you're right. This may be a bit better. Let's do this. Yes. Okay. You can always cut somehow your thing. Like this. Yeah, you're right. Maybe this is better. You just, you have like this very small cylinder. And then what you get is M10 composed with M02. But no, it's the same problem, right? It's the same problem that you don't get the same numbers. Sorry. I prefer this picture. M0 and 1, so it's the same problem here. So you have 1 goes to 2, and you have to compose them. Well, maybe let's think about this afterwards, but I'm pretty sure that there's one.
0, 2.
No, because I mean, I should not write 1 here, right? I should write 0.
Yeah. But then you're like contracting over the repeated 1.
Yeah, that makes sense.
Compare it, which says like Vm only depends on the topology.
Yes, but it's true that you should have, I think, the same boundaries. I mean,
How about you actually ignore the boundaries and just go back to dealing with the cobordism correctly via 4?
I can do 4, yes.
No, but like, don't read them as labels, just read them as cobordisms, because these are just labels.
Oh, yeah, okay, good point, yes, okay. So we know actually that M0 and M1 as manifolds, anyhow, they are diffeomorphic. So actually, yeah, I can call it 1 or 0, actually. But what's important really is the linear map. So we have something, this cylinder, which composed to anything gives this anything. And yeah, this implies then that a cylinder is the identity. So this implies that V of cylinder is the identity. somehow what we're doing here is just sanity checks, more or less sanity. Another thing, we can reprove, I mean we already proven it actually, that this is K. Empty set is K, so we have already seen the argument, somehow it really reflects the third axiom. If you take the union with empty set, you get the same as just M1. So you have this identity element of the tensor product. And the last thing, which is kind of for mathematicians very interesting, is that whenever B is closed, if B has no boundary, what happens actually? Imagine you have like this object. What does it correspond to? What's its incoming boundary? Empty set. So B, the empty set is K. What's the outcoming? Same thing, empty. B of empty set is K. So what is the TQFT assigning? This assigns a linear map between K and itself. And actually the homomorphisms between K and K, well, if you want the K homomorphisms, this is actually just K. It's just multiplication by some constant. Yay. And this is actually, I mean, it seems very trivial, but it's actually very important because it means that to a closed D plus 1, what did I say? It's D, I think, right? Yeah. So to a closed D-dimensional manifold, I associate now some variant, like V of B is actually an element of K, and this is an invariant. It's invariant under homomorphisms. This is kind of the first axiom. The first axiom tells you that the thing you associate to a manifold and also to a cobordism is invariant under the topology. I mean, it's only a topological invariant. And this is actually how you get, from the mathematical perspective, these kind of invariants of manifolds. Topological invariant. Of B. And you have actually a way to compute it, because even this kind of cobordisms you can read. You can read this thing, like you start from nothing, then you have like kind of a first non-trivial thing, which is kind of this creation. It creates from nothing something, and then you just go through all the critical points, and you have all these kind of interesting things. You have like a vector space, then tensor product of two vector spaces, and you go through it, you read through it, and at the very end you have some kind of operation which, I mean, you have creation and then annihilation at the end, and just reading it off gives you some number, and this number is the topological invariant. And typically, well, maybe I should say that I think even Atiyah, he does not speak about vector spaces, he speaks about modules over rings. Because actually it's just a generalization of a vector space, not over a field, but over a ring. And typically a ring we like a lot is the ring of polynomials. So if you have some polynomial ring, for example, like over complex numbers, then typically reading these things gives you an element of this polynomial ring, so it associates a polynomial to your manifolds. And yeah, this is like how you would use it. Questions so far? Almost done.
Are these polynomials the same as the ones for knots?
Almost. We will see this in the third lecture. But there is, if you take this definition literally, then it does nothing to knots. You need something, you have to generalize it. But it's actually a good question because it comes exactly to the last subsection, which is 1D TQFT. TQFTs. So let's see how that works, like, yeah, in the easiest example, which is one-dimensional. So one-dimensional means that the cobordisms are one-dimensional, so the actual manifolds are zero-dimensional. What's a zero-dimensional manifold? Just a point, yeah. So zero-dimensional manifolds, well, it's a disjoint union of points, but if I just take it's just a point. But you should equip it with an orientation. So it means actually that it comes with either a plus or a minus. And so your TQFT should associate some vector space, which I will call V, to the point with the plus. And then by axiom 2, what is this vector space? This is just the dual. Yes. Changing orientation, just take the dual. So now you literally see actually how tensors enter the picture, because now a zero-dimensional manifold in general, it's like a collection of points plus and minus signs. And so like your incoming boundary somehow is like just a tensor product of V's with V inverse. Let's keep the axioms for now. Okay, and what are cobordisms? Well, cobordisms, like the basic cobordism is just a line. It's just an oriented edge. Oriented edge. But actually, yeah, we will actually drop all the orientations, because if you want to be exact, then the induced orientation here is a plus. And I think it should be a minus. Yes. So now we can actually go through the list of possible cobordisms, because you can actually have different signs, right? So I think I wrote it with a small v, right? Small v of plus plus this is kind of a cylinder. This is just the identity.
Minus plus, no?
No, because what we said is like the induced thing here is minus, but since it's the incoming thing, you have incompatible orientations. Remember I said it's a map from B minus to D plus. What I draw here is the induced orientation.
Got it. Yep.
But what I impose as orientation is plus minus.
Absolutely.
Well, that's the point. Well, the same argument gives you. So yes. So the same argument gives you. If I do it the other way around, and I put minus signs. So the same thing, it's identity of star. Well, this is what I said earlier, that somehow if you just reverse everything, it gives you the same kind of object. And then you have two more. Well, one I will write like this. So I have plus and minus apparently, if I'm not mistaken. Plus and minus. So now, the induced thing here is minus plus, so they're both incompatible, so they're both incoming. And the last thing should be the opposite. This, where we go from minus to plus. So and what should this be? Well, it's a map from V tensor V star. Right, we have two boundary components, they are disjoint, so you have the tensor product. And it goes to nothing, right? You have nothing here, so it goes to K.
Contraction of the scaling.
And this is exactly the contraction. Yes, it's called contractional evaluation. So if you have a vector v and some linear form phi, it literally gives you phi of v. Called evaluation map. Evaluation. Now let's evaluation. Or contraction. This one I'll draw it again because this is actually an important one. So now we have two outcoming things and nothing incoming. I said it's minus plus. So now it goes from nothing. It goes from k to, well, v star tensor v. V tensor star. And yeah, this is called the co-evaluation map. Co-evaluation. Co-evaluation. But before writing down like the exact map, well, one important remark is actually these four things, they're all the same. Because somehow, I mean, it's just an edge. The edge you can like somehow just change orientations, just declaring like what is incoming, what is outcoming. But they're all the same. So somehow the evaluation map, we all know from linear algebra, it really corresponds actually to the identity map. So earlier I told you that v star tensor v, this is isomorphic to pom v comma v, right? And there is of course the identity map here. And actually you can check that if you take the identity map and you look what does it correspond to through this isomorphism, it literally corresponds to this evaluation map. But you could do the same thing and deduce what's the co-evaluation map. And the result is the following. Well, it's a k-linear map, so it's sufficient to tell you where 1 goes. And 1 goes to something I write like this. It's ei tensor ei. So unfortunately, in order to write this expression, I will choose a basis. Ei is a basis of v. And E upper I is the dual basis. Somehow, yeah, in order to write anything, I have to choose a basis, but it's actually very important, and you can check this, that this, the final object here, this is independent. This is independent of this choice. Independent on the choice of basis. Some people call it the Euler element. But anyhow, like really, it is nothing but the identity map through some kind of isomorphism, like, considered a bit differently. And that's actually all, right? I mean, your one-dimensional TQFT, we will erase this for, your one-dimensional TQFT is nothing but combining all these things. I mean, this is kind of the basic building blocks are just these edges. So now if I take some inputs, some outputs, what could I do? I could maybe assign things like this. I could actually cross. But the cross literally just exchanges vector spaces. Like the crossing literally is the map which to two vectors associates the other one. So it's really the swap. So you have all these vector spaces here. Let's say v, 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 v. Actually, yeah, the only interesting thing you can do is actually, well, in this picture it's really just the identity. The interesting thing you could imagine is something like this. Then you have something like v and v star. And then the only thing you can actually do is kind of some evaluation. Or you could also imagine somewhere here. And then you have this co-evaluation. So the only things you have is co-evaluation. Sorry, this is co-evaluation. And somehow you can check, well, the axioms. Like we associated linear objects from linear algebra to our manifolds and cobordisms. This somehow is built in, this is built in. Well, there's not really gluing happening. Well, you can glue identities together. So everything is satisfied. So somehow the summary of this example is a one-dimensional TQFT basically is in bijection just with vector spaces. The only choice we ever made here is V. Once you have V, everything else is determined. And this is actually a good point to start. Welcome back. So, if we're going to 2D, there's this one exercise. In this one-dimensional setting, there's actually one kind of cobordism we have not drawn, which is just a circle. So this should correspond to some number, right? So what is this number? Let's draw the picture maybe a bit larger. So it's a cobordism between what and what? Empty set to empty set, right? So it goes from K to K. So the idea somehow is to read this picture, so you should actually cut it in half. What's the vector space in the middle? You have 2 points, and you have this. V cancel the dual, and then you have these 2 maps. So this map, I think I erased it. This is, well, there's only one map between K and this V tensor V dual. This is the co-evaluation, and this is the evaluation. So if I really want to write it down, well, I just can check what happens to 1. It goes to this kind of Euler element, sum EI tensor EI. And what's the evaluation? This is co-evaluation. And what is evaluation doing?
We contract.
You contract. So it's just the sum of EI, EI. This is just 1. This is just 1. So what you get at the end is, well, I have not specified from where to where the sum goes, but you have a vector space V, and EI is the basis. So actually, this is the dimension of V. So this is the very first example where you really scan through this manifold, this circle, you write down kind of these maps, co-evaluation, evaluation, you get out a number, this dimension of V, and this is, this number does not depend on how I draw the circle. So this is the invariant of the circle. So V of the circle is 1 is dimension of V. So it's not very strong as an invariant. Anyhow, actually in dimension 1, the only closed manifold is the circle, so you cannot really, there's nothing to distinguish it from. Okay, but here you have like a first example how TQFTs work. Okay, so now everybody is back. No question? Yes? No?
Just a small question. If the dimension is 1, do we have problem with the invariance in the case that since we multiply invariance, then we'll get that 2 circles will get still 1? Or am I, like if we do a figure 8, right?
You mean like what happens if I have 2 circles, for example? 2
circles and the vector space chosen is just K again, right? So the map will be 1 and the multiplication of 2 will be 1. So can we, maybe unless I did it wrong, we can differentiate the 2 circles?
That is a good question. Like if I take 2 circles like this, yeah, then it's still it's still a map from, well, K, tensor K, so it's still a map from K to K. But now you have two evaluations. I think this, yeah, this should be dimension V squared, right?
Yeah, but if its dimension is 1, then we can separate.
Sure, yeah. But I mean, you have different choices, right?
Yeah,
You just choose a TQFT, which is slightly more difficult, and then you can actually distinguish between these two. Yeah, it's okay. That's good point. This one. Okay, yeah, well. Other questions? And we're ready for the second part, which is 2D.
Sorry. Maybe you said this, but so the conclusion is that it like there's like equivalence between 1D TQFTs and vector and finite dimensional vector spaces, right?
Hilbert spaces with unique dimensions. I mean, you can like write down the axioms with like Hilbert spaces, and then because then you have the dual.
But if you just split it in vector spaces, then it's just 1D TQFT vector space.
Like yeah, 1D TQFTs is the same as. And somehow the invariant of the circle gives you the dimension of the vector space. Okay, so the whole second part will be about 2D TQFT. So there's apparently a lot of things to say. So first of all, what are the basic elements? The basic elements are closed one-dimensional manifolds. So closed just means that there's no boundary. But actually, one-dimensional manifolds, there are just two. Actually, that's like the line and the circle, but the line is not closed. So actually, there's only one such element. There's just the circle. So there's just the circle. Well, there's the circle which can come with two kinds of orientations. So the vector space associated to, say, the circle, you're going in the trigonometric anti-clockwise direction. So this will be some vector space, A. And then, of course, if I turn it around, this is just A. So again, this is really special to 1 and 2D. In 1D and 2D, there is actually just one manifold. There's only one kind of space. And so all these get the same vector space. If you take like higher dimensional TQFTs, then you have different kinds of manifolds, so you have different vector spaces. Here we do. And what is a cobordism? So I just say explicitly what the definition tells you. So it's an assignment which gives a vector space to each closed one-dimensional manifold, and the cobordism is just a surface. But it has to be oriented. It has boundaries. It can have boundaries. But typically, such surfaces, they are classified by two numbers. Actually, these are the two numbers you have seen in Edwards' talk, G and N. So you have a genus and a number of boundary components. Genus and boundary components, the number of boundary components. So the pictures we will draw, they look like this. I mean, they look actually exactly like all the pictures I already drew so far. Something like this. These kind of pictures we will draw. And in this specific case, well, again, I will not draw the orientations, but everything to the left is one thing. So here we will have A tensor A, and we have some linear map to A tensor A tensor A. Somehow we will never really use the dual, because whenever you have something which comes with the dual, you can just somehow bind it around, and it just changes its like incoming to outcoming, or not incoming to outcoming. Okay, and so now, really the most important idea of these TQFTs is that we want to decompose these cobordisms, and we want to decompose them in like simple pieces. So the question are, what are the elementary cobordisms? You all agree that this is not elementary, what I draw. Much simpler things. So for example, in this example, what is like the first thing I should do? Well, if I cut here, of course nothing happens, it's just two cylinders. So as you already said, somehow, if you know about Morse theory, so whenever you have critical points, something interesting will happen. So the first interesting thing is this slice, which looks like this. You have two inputs, one output. So it's a map from A, tensor A to A. This we will call the multiplication. This is like the first one. So somehow what we will see is like in 1D, we had this vector space associated to the point, and there was no other restriction. Now in 2D, well, there's just this circle, which also gives you a vector space. But now actually these kind of cobordisms, they give you extra structure on this vector space. And the first structure we have is this multiplication map, something which takes two entries and one output. You should really think about it as a multiplication. A, B goes to A times B. But somehow this lives on some kind of vector space. So one reason why we call it the multiplication is that this multiplication is associative. Oh, I give it a name. How do I know? I denote it by M. M like multiplication. So M property, M is associative. So remember, what does it mean? It means like, well, if I first multiply A and B, and then I multiply it with C, should be the same as first multiplying B with C, and then multiply it with A. If you, like, this writing of M, like I can also write it as A, B, C equals A, B, C. This may be, like from numbers, it's more like this property you have in mind. So how would you prove this? So we'll see a lot of properties, and also, for example, exercise 2 of this sheet is like a whole bunch of strange identities which are horrible to read. And the basic idea is always just draw the picture. Just draw the picture. So what happens? So you have M of AB. So how should I write this?
Join A, B.
Yeah, you have A, B, and C. A, B, C. And so we do first A times B. Somehow to C, for now we do nothing. Nothing is the cylinder. And now we multiply the result, A times B, with C. Multiplication is just this thing. So this is the picture which corresponds to this side of the identity. So I give you some time, let's try to draw the other side.
Yep.
Three inputs, ABC. And now, well, you just exchange actually these two. So you first do BC. A, and then you combine these two. Well, now I have A with BC. Here I have A, B, C. And actually, if you look at these two pictures, like now you should really think about them just as topological objects. So you can actually just deform them. Here you have like a small valley and then a big valley, but actually you can just push this and get a big valley here and a small valley here. So these two things are topologically equivalent. And by the definition, like by the axioms of TQFT, these two things, since they are topologically equivalent, should give the same answer. So you get this equality sign. Yeah, the first time I saw this, I was really amazed, because it really means that also, from the other perspective, now you can actually give like a diagrammatic way of multiplying things. Nice pictures instead of multiplying. Okay, so this is the first elementary cobordism. Well, the second one is pretty much the same, but reversed. It's actually, I think, what happens here in this map. So we had like 2 to 1, but the next slice would be here. It is 1 to 2. So it's the next cobordism. So it's a map from A to A tensor A, which I denote by delta. And without surprise, this is called the co-multiplication. Some people call it the co-product. Oh, but just to be coherent, multiplication, co-multiplication. Like for those who know a little bit about category theory, it's really like you take the same thing here, but you just reverse the arrow. So. And, well, we will not prove it, but actually if you just take these pictures and you reverse everything, then proposition, the co-multiplication is co-associative. So if you don't know what co-associative is, well, you just literally take these pictures, you reverse them, and you can somehow read off actually the equation you would need. Yeah, I will not stress on this too much. So. As a first remark, now we can already give actually somehow a meaning to what you might actually think is an elementary piece. Right? We saw that, like, if you take a cylinder, it's just the identity. So if you take the linear map associated to this kind of cylinder with one genus, so this actually you can decompose, right? You can decompose it like this. So the first one is a multiplication, so it's m, and then you compose with delta. So again, the linear map associated to this kind of torus with two boundary components, it's just the combination, the composition between co-product, co-multiplication, and multiplication.
The other way around?
No, because like when you compose functions, you read from right to left, unfortunately.
Starting from 1 and going to...
Oh, sorry, you're right. Oh yeah, that's true. Yeah, no, this was here, you're right. The first part here is delta, and then it's m. So you reverse them. Did I write this wrong? Oh, no, yeah, I just... Okay, and there are two more basic cobordisms. So for this picture, do we need more? Like here we have multiplication, co-multiplication, multiplication, co-multiplication. I think at some point there's something new. Because you go from here to, I mean, you have two boundary, let's see.
Very close.
Yeah, you have, yeah, I should do it like this probably. Yep. You go from here. 1 to 2.
New.
Oh no, it's new.
You can just do code multiplication twice.
Yeah, no, no, nothing new here. Okay, so you might imagine that. But how do you do the sphere, for example? Just the sphere. How do you decompose the sphere? It goes from nothing to nothing, but somehow something happens in the middle, right? So there are two more actually things. One thing looks like this. So it's a map from nothing, so K, to A. I will call this epsilon. And this is called the unit. And this is actually another reason why we call this a multiplication, because it's not only associative, it actually has a unit. And we will prove that this is the unit. So it is really the unit of multiplication. So what does it mean? It means whenever I multiply with 1, so what is 1? Well, you should actually think about this like epsilon of 1 is somehow the unit element of A considered with this multiplication. Well, this is actually already the proposition. So what does it mean? Well, it means that whenever I multiply this to anything else, you should get this anything else. You should act that identity. So let's try to do a picture. So epsilon of 1 is this picture. And we want to start with some element, A. And now I want to multiply them. Multiplication is this thing, right? So here now I have epsilon of 1. Well, if I start with 1 here, I have epsilon of 1. 1 is element of K, A is element of A. So if I multiply these two things together, I should get A. Do you see why?
It's a cylinder.
Exactly, yeah. Topologically, this thing is this is just a cylinder. And the cylinder, it goes from A to A. It's just identity. This map is just identity. So actually, personally, I really have troubles actually to write down the equations. So I would draw the pictures first. But now that we have the pictures, we can actually exactly write down the equation. The equation is as follows. So we start from A. And then, well, actually, if I want to be very precise, I should actually add another cylinder here. So I do nothing and epsilon. So I have identity on A, tensor epsilon. Now maybe we have never seen this, but whenever you have like a cobordism which actually has two pieces, then somehow you just take the tensor product of the two linear maps. So you have identity here, epsilon here. So this map goes from A to A tensor A. And then you compose this with multiplication. And this is actually identity. So, yeah. Actually, the proposition, the fact that this is the unit element, is actually this. But yeah, I'm unable to write this like out of my head. I will first actually draw the picture and then write this. But yeah, like somehow exercise 2 is to do the opposite. Like to just start from the equation, draw the pictures, and show that they're topologically the same.
And that holds for any element of K, not just one, right?
Sorry?
Sorry, it holds for any element of K, not just...
That's actually a good question, because like, of course, if you have a 2 here, then you get 2 times A, not A. How do you see this?
As a vector space, 2A is just A.
Again?
As a vector space, depending on the field, yeah.
No, I think 2 times A is like literally, I mean, the vector space comes with an action of the base field. Oh, maybe.
I mean, take C to the n, for example, multiply it by any real, any complex, still C to the n.
At the end, you get a map from K tensor A to A. K tensor A. Well, my guess would be like if you have an element K here and an element here, this should give you K times A, right?
Yeah, it is.
So it's not identity.
I think maybe it would be because you can always absorb K's cross A to just be A.
Yeah, exactly. This is isomorphic to A, and in this isomorphism somehow you choose small k to be 1 somehow. Yeah, probably. Yeah.
You choose Ka to be the element rather than A, and then.
I mean, somehow you could say that it depends on your isomorphism. Like, if you do this isomorphism with an element, for example, if you do it with 2, then actually this proposition is wrong, and it's epsilon of 2, which is the basic element. Somehow, yeah, the way you identify these things gives you actually the unit element.
Identification just multiplication by K as a vector space.
Oh, you mean like this map is actually the identification?
Yeah, exactly. This is the isomorphism that should define
okay.
the tensor product.
Oh yeah, you're right. No, sure. Yeah, this is the identification.
I think it's fine because you're acting on the left.
No, yeah, you're right. This is the identification, and then well, yeah, then epsilon of 1 is the unit element. But what should I write then? Then this is not identity. Right? This is some.
You're acting
by K in the vector space.
Yeah, something like this. Yeah, this is like the. I don't know. A tensor A. No, this is not. Yeah, well, I will write the identity of A. But yeah, it's actually not a vector identity. It's true. Maybe. But then from the TQFT perspective, this is really the identity, right? I mean, this is really the identity.
I mean, not really, because you want the diagram to commute, so it has to be like multiplication. A goes to AK. Otherwise, the diagrams don't commute anymore.
Like you start with Ka and end with Ka, so it's.
Yeah, but still, I mean, like, well, here I chose an element, but if you don't choose the elements, this is the same picture as this, and then you know that the TQFT gives you that.
I think the idea is that maybe the drawing tells that the map from AK to A is the same as the identity. A tensor K to A, and maybe that's what the drawing means, not necessarily by choosing an element, but the same way K tensor A is isomorphic to A, this drawing tells us that the map from A tensor K to A is the same map, is the identity on A to A, up to the isomorphism. Maybe.
Shouldn't the right-hand side be a map from K to the homomorphisms or the endomorphisms of A? Because for every epsilon, you have to implicitly choose an element in K for which to do this whole thing?
Yeah, sure. Like when I write this, actually, this goes from K tensor A to A tensor A.
So the right-hand side.
You mean that? Oh, I see what you mean. Actually, here I should actually write the nothingness. I should actually write it here. So it's actually not the identity between. Okay, I see now what you mean. Yeah. So it's kind of the canonical map. Yeah. Okay. It's the canonical map between K and A. Yeah. How to write it, but yeah, I mean it's exactly this, right? It's the canonical map between A to A, and this is actually exactly the multiplication map. Well, the scalar multiplication map. Yeah, okay. And then if you put K equals 1, then this is the unit. Okay. No, this is actually good, it's a good remark. Like whenever you compare cobordisms, you should somehow keep the same income and the same outcome. Like here the income is nothing and A. So actually here you need nothing and A. Yeah. Okay. Okay, and then the last elementary piece, well, it's pretty much the same thing as this, it's just the opposite. It's this one. So it's a map from A to K, which I will call eta, I think. Yes, eta. And without surprise, this is called the co-unit, because it has kind of the same kind of property with respect to the co-multiplication. So here is 4 elementary pieces. Question: is the multiplication commutative? So we have shown that there's an element, a neutral element, a unit element. We have seen that it's associative. Is it commutative? Let's make a poll. Who thinks that it's yes? Very few. So who thinks that it's not commutative? Also very few. We'll do a democracy with you. So let's draw the picture. So you ask somehow, is this picture, so this is A, B, is this the same as, well, we should put in the same things, but you should first cross somehow, right? You should first cross, and then combine. Now I have A here and B here, so I have B times A. Are these two pictures the same?
Only really if M, if the action of M and then delta is the entity. If the co-product of the product is the identity, then it should be, otherwise not.
This one, M and delta?
Other way around, sorry. If delta, no, yeah, M delta. So delta circ M, if that's identity, then it should be fine. Then your cross is just 1.
No, it has nothing to do with this.
No, he's not referring to that. He's referring to first.
Yeah, but even no.
So the one on the right is not flat, no?
Sorry?
It's topologically not the same thing because it's not flat. I mean, you can't compress it to a flat surface, because they cross. I mean, it's like planar diagrams and not planar at all.
Okay. Well, like, at this point, I really should warn you. Like, we draw these pictures as if they lie somehow in R3. But actually, it's really just topology. There's no embedding here. So actually, when I cross, nothing really happens. I mean, you could imagine that it crosses in front of you or behind you, but there's no embedding. It's the same thing. So what you can do topologically is really just you take this piece and you just turn it around somehow. It undoes this thing, and topologically it's a homomorphism. These two things, they are homomorphic.
So when you draw a cross, you're thinking them essentially being like one of
Yeah, that's why I literally, I mean, that's why I draw it like this. But they don't intersect. I mean, it's just the way you draw. Yeah, somehow. It's just a picture. It's just a picture of something which actually, you can imagine that it lives actually in 4D, and in 4D you can actually somehow cross things. Or, I mean, it's really just a picture, so maybe I should write this, attention, there's no embedding in these pictures. No embedding. Like something like into R3 or something in these pictures. Yes.
When you say that we need to be homeomorphic, do we need the homeomorphism to be orientation preserving?
Oh, yes, yes, yes. Yeah, it's oriented manifold, so it's orientation preserving. So there's no embedding here, but that's actually very nice. I mean, maybe you're all shocked, or many of you are shocked, but it's actually a good point, because we will see in the third lecture that you can actually you can modify the axioms a little bit, and you can actually impose these cobordisms to live in some ambient space. Then you can maybe make this more interesting. You can actually distinguish like this crossing from this crossing. So we will see this in the third lecture. Right? If you just take the TQFT literally, just about topology, no embedding, nothing, so these two are the same. So the answer is yes, they are. It is commutative.
This is a product of the choice of tensor product, right?
Oh yes, you can ask, yeah, it's a good question. You can ask what is this elementary piece actually doing? It's a map from A tensor A to A tensor A, and it's literally the swap. It's really the swap. So maybe I should write this down as well. Yeah, we'll erase there. This we will not consider it an elementary piece, but actually this is a map from A tensor A to A tensor A, and it's literally A tensor B goes to B tensor A. So it's really the swap. It's nothing more. And somehow we will see tomorrow that you can make this swap more interesting, something which is not just swapping things.
Does this mean that we have essentially a bijection between two TQFTs and commutative algebra we can put on A?
Not exactly. We will see the algebraic structure right now. Yeah, it's not. It's a bit more, because yeah, there's one more thing we have not drawn yet. There's one more property. I mean, well, we have these four elements: multiplication, unit, co-multiplication, co-unit, and we have not explored all possible pictures for now. To see like what are all possible relations between these things. So we have seen that the unit is a unit, the co-unit is a co-unit, but that's actually one thing more.
I couldn't see why we draw this cross cylinders, because isn't it just BA?
Isn't it just BA?
Isn't just BA going to BA?
This is a cylinder, so it's the identity. B goes here, A goes here.
But we are looking at MBA, right? So why, like, we are going to
here. Yeah, if you want, this is M of AB, whereas here this is M of BA. And since these two pictures are the same topologically, the result is the same.
Yeah, I understand, but why do we drawing these cross?
Okay. Well, for some reason, like when I draw this picture, it's always the thing which is on top times the thing which is on
okay,
top.
Okay, I see.
That's just a convention. So, like, if I want to swap them, I have first to swap them and then back. Yes.
In this picture over here, would you not need to like dualize the? Was there an outgoing then?
It depends how you read, but if I really read from here to here, I mean, I have not drawn the orientations, but if I draw the orientations correctly, such that these are AA and AA,
then the actual elements would.
Okay, so now we had this question, like, what's the algebraic structure? Is it just an associative commutative algebra? It's a bit more, something called a Frobenius algebra. So yeah, literally what it is, it's the algebraic content. Literally, this is the algebraic content of 2D. Follows a Frobenius algebra is so it's a vector space A equipped with a associative and unitary. Oh, wait. wait, sorry. Well, in the definition of a Frobenius algebra, you don't ask it to be commutative, so that's not exactly true here. Well, let's say it's almost. So a 2D TQFT will correspond to a commutative Frobenius algebra. But, I mean, we will write this theorem. Vector space equipped with A associated with a multiplication. And, yeah, there's one thing more. And a pairing A tensor A to K. It's a K vector space. So we call this sigma. So whenever I say pairing, this is like somehow always the case. It's always non-degenerate. And bilinear means that it's linear with respect to each factor. Non-degenerate means that, well, whenever I fix one element here and you get 0, then actually this element is 0. Such that, so there's one condition, which is the following: it's sigma of ABC equals sigma of ABC. This is called the Frobenius identity.
Shouldn't it then be like a product A?
Oh, well, yeah, I mean, I use A times B as the multiplication. If you want it should be sigma of M, A, B, comma, C. Yeah, I mean, here, good point. Yeah. A, B is shortcut for M, A, B.
No, so I mean the domain for sigma.
No, it's from A tensor A to K. This is an element of A, this is an element of A, this is a scalar. This element of A, this element of A, you get a scalar. Scalar equals scalar. I have not drawn now, I haven't drawn what the picture of sigma is yet.
Okay. So it's okay to replace the comma with the tensor product?
Here?
Yeah.
Oh, yeah, I see what you mean. Okay, yes. So a bilinear map between A tensor A to K is actually the same as a linear map of A.
A bilinear map from A cross A is the same as a linear map and A tensor A.
Oh, you're right. Yeah, no, you're right. It's actually this. Yes.
That's basically the universal.
No, it's true. Yeah, but then, but sorry, but I love tensor products. I should not call it bilinear. I call
the commas become tensor products.
Yeah. Okay. Yeah. I like this. Okay. You can have both. Yeah, you're right. Okay.
Just choose a convention.
Well, my convention is that I like tensor products, but I don't like them on
arguments.
Yes, okay.
We like tensor products, but don't like drawing them.
Yeah. No. No, I've never seen this like this, sorry. I would put the comma.
Mostly understood from
okay, then I will just comma. Aim now somehow for the rest is to show this equivalence. Like, how do you go from a Frobenius algebra to a TQFT, and how do you go from a TQFT to a Frobenius algebra? So one way is easier than the other. So the easy part is going from a TQFT where you have a lot of data and you extract the Frobenius algebra. This is easy. The other way around is a bit harder because you have to reconstruct all these basic cobordisms from somehow just these two data, which is the multiplication and this. So let's see, how do you go from a TQFT 2D to a commutative? So the TQFT already gives us a vector space, right? D of the circle is A. And we have already seen that there is a multiplication. we have seen that it's associative and unital. So yeah, so we should say what is the pairing? What is sigma? What is sigma? So sigma, well, we should actually write the picture first. The picture is it goes from A, well, tensor A, to nothing. A to nothing. So how should I draw the picture? Yeah. So this is sigma. But how, I mean, we have not introduced this before, right? It seems to be an elementary piece, but it's not. It's not because, well, you can cut it here, right? So what is it actually? It's this combined with this. So actually sigma equals, so first the multiplication map, and then the co-unit, yes, which is eta. Okay, and let's now exercise proposition sigma defined like this satisfies the Frobenius identity. Right? If you prove this, then we are somehow done with this first direction. It shows that you can extract this Frobenius algebra structure from the TQFT. So I give you some minutes, try to draw the picture of this identity and show that it's true. Just looking at the picture.
One minor detail. You used A tensor A down there, and I'm confused how I should get from A equals A to E tensor.
Yeah, I mean, no, this is
but on Wikipedia, that's correct.
Remark, I don't know where to write it. Here. Remark, a bilinear map, I should write it like this, bilinear map between A cross E to C. The set of bilinear maps of A cross B to C is actually the same as linear maps between A tensor B.
Thank you.
So you can simply somehow, you can, or the other way you could say it is there's a unique extension of this map to A tensor A, which is linear. And I still call it sigma. And this is the sigma I defined here. So yeah, but it's a good remark. Is it to answer the question, or is it a question? Yeah.
Do you have a co-unit in the Frobenius algebra?
Not in this definition. That's why the other way is harder actually, because you have someone to construct the co-unit and all this stuff from this data. Yeah.
It's almost the same about the co-algebra structure.
Yeah, I mean, it does not come with a definition, but you can define it. You can extract it from the Frobenius algebra. It's not difficult, but we'll see this. Frobenius algebra. Frobenius identity. Oh yeah. Okay, let's see. So we have ABC, right? ABC. C. So the first thing we do, we multiply A and B. Strictly speaking, we do nothing to C. And then we apply sigma. Sigma is this kind of thing. So I will just use it as a building block now. This. And on the other side, also ABC. Now I will first multiply A with B, keep A, and then I use this. Right? And again, this kind of picture we already saw when we did this associativity. You have like a small and a big thing, but you can just topologically remove them. This is topologically the same. So this gives you exactly this Frobenius identity. Sigma of ABC equals sigma of AB. Yes.
Can we think of sigma as a kind of evaluation map, or because we don't have a dual A, it's not kind of?
Yeah, no, it's a bit different. It's a bit different. The evaluation map would be if you have A and A dual. But somehow, why I'm never writing the duals, because somehow A dual, this picture, is literally this picture, which we use from A to A, which is just identity. Yeah. These evaluation maps, it's just identity, just other avatars of the identity. And we can actually use this in order to put all the A's on one side and all the other A's on the other side. Yes.
Do you have one concrete example of Frobenius algebra?
Very good question. This is the next part. The next part is examples. Yeah. Who cares about examples? But yeah, no. So the first thing I wanted to show you is that that the TQFT gives you a Frobenius algebra. So now we should discuss some examples, which actually then gives you. And then we want to show that you can reconstruct the TQFT from this. So yeah, examples. Let's see some examples. What's the easiest? I think one of the easiest, but which we will not really consider here, is matrices. Matrices, they have a multiplication, and as sigma of AB, I take the trace of the product. So of course, if you take the product, and then, I mean, if you check the Frobenius identity, it's almost saying nothing, because it will tell you that trace ABC equals trace ABC. It actually just tells you that this matrix product is associative. But for all these examples, we should check, is it commutative or not? So matrix multiplication is not. So this is a very nice example, but unfortunately it will not appear in the kind of strict sense of TQFTs. But we will use it probably tomorrow when we do this kind of embedded stuff, where things can, things become. A whole list of examples, but many, no, some of them maybe some of you will not exactly understand what doesn't matter. So another example is you have a finite degree field extension of A. So A is K. So K is some field, and then there's this theory of field extensions. Like, for example, if you have like rational numbers or even real numbers, you can, for example, have complex numbers, or well, complex numbers is not finite dimension. Sorry, you should take something like. Sorry. Complex is a two-dimensional extension of the real numbers, and yeah, this kind of stuff. So we have like another field now. This is a vector space.
Yeah, field extensions are vector spaces over the base field.
Yeah, sure. Oh yeah, exactly. Yeah, exactly. Field extension is actually a vector space over the base field, and so it's a K vector space. Oh yeah. So okay, yeah, it is a vector space. It is commutative because fields are commutative. Yeah, that's why I think I included this example because we will not use it, but it's a commutative example. Well, and I should give you the formula for some sigma of A comma B. Well, it's kind of the same kind of idea. You use multiplication, and then epsilon is any map. Epsilon is a map from A to K, and it should be any non-zero K linear map. Any non-zero K linear map. Well, so this is literally an element of the dual, right? So it's just some linear functional on A combined with the multiplication. Yeah. Okay. I have another example which is quite evident. Quaternions, you have multiplication, and again, sigma of AB will be the real part of AB. For those who know quaternions, you have like, it's a four-dimensional R vector space. You have 1, I, j, and k. So the real part is kind of the coefficient in front of 1. And, well, it's kind of the same kind of examples as here. The only difference is that quaternions are not commutative. Go through the examples a bit quick because actually we never use them. But I want to show you that there's actually a bunch of examples. So another example which is kind of very common is you take a group and you take what's called its group algebra. So maybe in order to make things simple, G should be maybe a finite group. Yeah, maybe G is a finite group. Yeah. Well, actually, it's not necessary, but let's say it's a finite group. So what is this beast? So it's simply like a formal linear combination of group elements. You can say something like G1 plus G2, but the plus is really kind of formal. And how do you multiply these things? An element here, an element of K of G is of the form some complex number AG G. So you sum over all elements in G, and AG is a complex number. K as in K. K is C, and just some linear combination, formal linear combination. Formal linear combination. Yeah, something like G1 plus I times G2 minus 3 times G3. Like this. And how do you multiply these things? Well, it's very natural how you would multiply these things. It's just by associativity, like let's multiply, for example, G1 plus IG2 minus 3G3. Let's multiply this with, I don't know, G4 2 times plus G5. What you would do simply is really just using distributivity. So it's like 2 times the element in the group G1, G4, and then G1, G5. And then you go here, 2i, G2, G4, and so on. So it's literally, you just multiply kind of formally these elements. This gives you a multiplication on this group algebra. And the sigma kind of the natural choice is, well, when you have an element AG, G, just associate the coefficient in front of the identity element. Somehow it's very similar actually to the quaternions. Because in the quaternions you have 1 I, j, k, and the real part is exactly taking the coefficient in front of 1. 1 is the identity element. And yeah, I mean, you can check easily. Oh yeah, maybe, sorry, this is, this is sigma, yeah. And then, well, sigma of AB. Oh, no, sorry, no. It's not sigma. Well, let's call it trace. This is trace of AB. So maybe, well, you might notice one feature that actually in all the examples, you always use actually the multiplication and then apply something. But this is maybe not surprising because it comes somehow from this picture, right? Like we always use some multiplication. I mean, we use the multiplication and then actually just some kind of co-unit, something which goes from your vector space to K.
I guess like the question now is, are all sigmas of this form? Like, can you find one that's not on this form? Probably the answer is no, because there is like a bijection there, but yeah.
Well, there's a bijection between 2D TQFTs and commutative Frobenius algebras. So,
okay, maybe
so
not.
Good question. Because somehow you could actually define eta maybe this way. You can define eta as being sigma times. Maybe I will answer the question later. I'm not sure. Maybe. One question we should answer is this thing commutative or non-commutative? It depends on G, exactly. It's commutative if and only if G is commutative. And now we get actually a bunch of examples. Like if you take any commutative finite group, or even infinite group, in the infinite case you just ask this sum to be finite. So you take like group algebras of Z mod n Z or things like this. Well, and I have a last example, which is just for those who understand or who know these things. So the last example is A is the cohomology of some. So it's the cohomology of the compact oriented manifold. Compact X. And multiplication is cut product and the sigma is integration. Just for those who know about these things. Is it commutative, non-commutative? It's not commutative. It's not commutative because A wedge B is not always equals to B wedge A, but actually it's something called graded. It's graded commutative. Every element comes with some degree, and then when you swap two things, it's a little bit like fermions and bosons. Like you swap them, you get either plus sign or minus sign. And actually you can somehow build a theory of like graded TQFTs, and then this would actually be an example of a simply graded TQFT. Okay, so yeah, again, sorry it's a bit quick, but yeah, it's just to give you a feeling of how the examples look like.
Wouldn't an easy example of a Frobenius algebra would just be R, equipped with regular multiplication?
Yes, and then the sigma is just multiplication again? Yeah. True. It's to be true.
Too simple to be interesting.
Maybe it's too simple to be interesting, yeah. Yeah, but I mean, isn't it like this example for n equals 1? Yeah, it's not commutative apart from n equals 1, in which you have just the base field and just multiplication. Yeah, no, but it's not. Yeah. So, Other remarks?
If you do A equals 2, then that kind of leads to quaternions.
To what? To?
Quaternions.
Quaternions. N2 of...
I mean, not directly, but like...
Isomorphic to.
N2 of R is isomorphic to... Because there are these Clifford algebras, and both of them are Clifford algebra. I'm not sure if they're... Okay, not sure.
But they're not the whole quaternions, they're greater. Obviously, like you can embed the quaternions in N2.
Oh, yes. Both of them are of dimension 4, so if you can embed them, I think then it's...
I think you need to take like unitary matrices.
Yeah,
sorry, Hermitian. Right. Hermitian.
Okay, so the last part before we go to eat is how do you reconstruct this? So maybe I should first state the theorem. The theorem is that there's a bijection between 2D TQFTs, bijection to commutative B algebras. In 1D, we just have vector spaces. Now we have these vector spaces together with multiplication and this kind of pairing. So we saw one direction, the direct direction, which is kind of not so hard. Now it's the opposite direction, which is a bit harder. Okay, so now somehow we have to reconstruct. Let's reconstruct the 4 elementary cobordisms. So multiplication, unit, co-multiplication. Okay, so let's go. M we already have. Comes from Frobenius algebra. Maybe I should say from A with M and sigma. So we start from A and sigma, and I have to reconstruct, well, M is already there, but you have to reconstruct eta, epsilon, and delta. So the second easy thing is eta. Define from actually the definition, which I just wrote. Yeah, just. So that's this kind of sigma. We saw that this is equal to eta composition with M. So if you have a TQFT, then sigma is defined this way. But now actually we can use this to reconstruct eta.
Isn't this back to the question of you can always write sigma like this? Like...
Oh yeah, that's true. So is there any detail? No. Is this obvious actually or not? I mean, I think you have to use somehow that sigma is non-degenerate. Oh. No, it's true, yeah, it actually means that. Does sigma actually, like, does sigma of AB actually only depend on A times B? It's not obvious.
No.
I have no more details here.
Actually, you can show it.
I think you can show
no,
it.
because B1 multiplied by 1, sigma AB is equal to sigma AB times 1, and then you can apply the rule.
Say it again, sigma of AB.
And multiply B by 1.
Where? Like here?
Yeah.
Oh, okay.
Then apply the identity above.
Sigma of AB1. This is nice, yes.
And now you can just say
well,
that.
I mean, now you see already that.
Yeah, it's product is what matters. Yeah.
Well, this is actually very nice because this is actually the definition of eta, right? Eta is a map from A to K, and it's just sigma of A comma 1. Oh, great. And then actually, defined, then we don't even need this. Defined by eta of A is sigma of A1. Great. Thanks. Okay, so then we have to reconstruct the old stuff. And now, at some point we really have to use this, the fact that this is non-degenerate. This is actually now. So sigma is non-degenerate is actually equivalent to the existence of something which I will call beta. Existence of somehow the opposite, like sigma was this kind of thing, and now I will call it this thing. This I will call it beta. So beta is a map K to A tensor A, such that, so there's a condition, keep the definition. Such that the following picture makes sense. So it's called a snake relation. Let's see why. We have somehow one thing like this and the other thing like this. This should be, well, identity of course. This should be the other way around. From this you can deduce the identity. The identity looks like identity A, or maybe some multiplication is equal to, so this is what I call beta. So I have beta with identity, beta tensor identity, and then I apply sigma, but on the other half, so it's sigma tensor identity. And it should be the same as if I do the opposite. So I do first identity beta, and then sigma tensor identity. So this might maybe come as a surprise. I mean, this beta, well, where does it come from? Like, this does not seem obvious that this is equivalent. So remark, why is this true? Well, actually, it's kind of gymnastics we did earlier. So we have this, the sigma looks like this. This is the sigma. This is we start from the Frobenius algebra. So we have the sigma. It's a map from A tensor A thing. This now is the same as, we can turn this around. So it's actually the same as the cylinder. But when we do this, now we have A star. So this sigma gives actually an identification between A and A star. So this is actually very natural. Like, how do you get this map? Like, when you take A, you associate the map sigma A dot. This is now a map which takes an element of A and gives you an element of A. And so being non-degenerate means that this is an isomorphism. This is literally the definition of what non-degeneracy means. So this is an isomorphism. But then, well, then you can do the gymnastics one step more. You can put it the other way around, like this. But now you have A star and A star. Right? So all these things are just different avatars of sigma. But now, since A and A star are equivalent, are isomorphic, well, now I can use this isomorphism. And I get a map from K to A tensor A. And this is exactly beta. So you see that the existence of beta is exactly equivalent of saying that this is here an isomorphism. And this kind of snake relation, well, it's just some kind of compatibility equation. Snake identity. Which comes actually from the pictures. Well, no, actually, when you start from a Frobenius algebra, you don't have the pictures. So you have to impose actually this kind of thing. But of course, you want to interpret it as a TQFT and then somehow you get pictures. So, yeah, sorry if I lost some people, you can wake up again. Just take this as granted. You have not only sigma, you also have beta. And now actually from this, you can somehow reconstruct the other stuff. So now let's reconstruct the co-modification. That's actually fun because you just have to draw the picture. I mean, you just have to draw the picture in the correct way. So we want to have this map, right? This is co-multiplication. And you want to write it using the building blocks beta, sigma, and multiplication. Somehow the only thing you can do somehow is you have to take one of these boundary components and push it to the other side. So topologically, this is the same as the following picture. So one boundary component here is income, identity. Then you create things. You create two more using, this is what? This is beta? Yeah, this is beta. And then, well, then you just combine these two by multiplication. You're going straight. These two things are the same. And here I only use kind of the building blocks I'm allowed. I have beta and n. So actually, if I want to write an equation, delta equals, I can write this here, so I have identity, tensor beta, and then I compose it with m tensor identity. So this actually, yeah, it's really funny actually to like just take these pictures and wiggle them around in order to like get to something you have in your as your data. And then, well, finally the last piece is then not very difficult. Finally, epsilon, the unit. So the unit, it looks like I have the same kind of equations here. Said that this is beta, this is the same as this. Probably it's the same kind of remark. Maybe there's a better answer actually. So you have beta equals epsilon and then co-multiplication. So how do you get epsilon out of this?
You start with epsilon?
No. It's unital. No, I don't.
Epsilon of 1 this way, you don't get.
Yeah, you just have 1, not epsilon. Well, but it's actually the same. Maybe you only have it. I'm pretty sure, like, how did we define eta? Eta was this. Maybe there's a similar guy. Like, if you define epsilon, so you want epsilon of 1, right? So you want to define epsilon of 1. So maybe this is nothing but beta of something. No, but beta gives you 2. No, beta gives you 2 star. I don't know actually. I mean, you could maybe if you apply beta to 1, get an element of A tensor A. No. Can you like then multiply, use multiplication afterwards? Yeah, I don't know.
Couldn't you just say that epsilon of 1 is the unit of your algebra?
Yeah, maybe.
You have exactly what you want.
Yeah, maybe. I mean, yeah, that's what somebody else said already. In the Frobenius algebra, you have actually. Yeah, maybe that's maybe it. Yeah. I should maybe check this. Okay, but apart from this, yeah, that's actually more or less all I wanted to say. Just wanted maybe to draw a summary on some blackboard. Let's see, summary. Second lecture. Well, just about it. One message is that the T2D TQFTs are commutative Venus algebras. And kind of the basic building blocks you have, you can actually interpret them both mathematically and physically. So let's see. So the table I will draw, it's from one of the references. So you have 2D cobordisms, you have algebraic operations. You have Feynman diagrams. And you have kind of the physical meaning, like kind of a principle, physical principle behind. Let's see this picture. So one of the basic building blocks was this picture. So the algebraic operation is, well, multiplication. A tends to A. So maybe a more schematic way of drawing this is this. Somehow you take the spine of this, and well, this is kind of merging particles together. And we have seen that there's a unit. Feynman diagram, you can see it like this. It's kind of the creation of a particle. Creation. Then you have the co-multiplication, somehow the two dual objects and the dual co-unit. Co-multiplication, co-unit. A to K, A to K tends to A. And of course, like if I really draw it schematically, it's this and this. So one of them is kind of the splitting, and the other is the annihilation. So I'm not sure if how literally you can take actually this picture. Does it mean something like maybe particle scattering is somehow linked to TQFT? Maybe not, I'm not sure. But I like this picture, so I wanted to share it. And yeah, that's all for today. So if you want, you can look at exercise 1 and 2 for tomorrow. And yeah, tomorrow we will somehow change slightly the axioms to make more interesting stuff in 1D and 2D. So we'll see knot and link invariants. And we'll also, we will revisit 1 and 2D, but with slightly different axioms.
Orange, the green snake relation, does that follow from nonlinearity, or do you have to impose this extra?
I mean, beta is defined here somehow, right? So this is literally sigma, but you use kind of these isomorphisms. This somehow you can define sigma this way, then you can actually check that.
This holds automatically.
It really holds algebraically. Yeah, perfect. And you can actually, like, if you don't want to define it this way, you can literally just take this definition somehow. Like, sigma is non-degenerate only if you have this kind of map which satisfies the snake relation.
Beta exists and it also has to satisfy this automatically. Okay, thank you.